So hello everyone, thank you for being here today. So my name is Helene Legros. I'm a postdoctoral fellow at the University of Alberta. And today I'll be talking about the work we've been doing at the Mantle Group, so at the University of Alberta. And specifically today, I will be talking about Paleo and Mesoproterozoic lithospheric modifications in the superior and the slave craton, and specifically looking at metals and rare earth mineralizations. So the Mantle Group is quite a large group. At the university itself, we have Graham, who's the main PI for this project. There is myself, Andy Dufresne, Jan, Sarah, Chiranjeev, and Janina, who's going to leave us soon, but also other collaborators from other universities, Steve Shari, Hendrik Falk, and Gideon Lemvik, and Dan Schultz. So we have different inputs here from the government, the industry, and academia. So a little reminder of why we look at the mantle. So we know that in this region, in cratons, we have some remobilization very deep in the mantle. This is what you can see here, for example, this metasomatized front, which represents remobilization that can create reservoirs in metals. And the idea is to identify these reservoirs that can be picked up by melts, just like this one, and then go to the crust to form crustal ore systems. If you look here at different types of ore deposits, some of them are known to be directly related to a deep input, for example, diamonds, nickel, copper, PG deposits, and rare earths, but some others are indirectly influenced by reservoirs deep in the lithosphere. For example, if you look at the affinity of different metals with different type of melts, some of these melts can have an input from the mantle. And this is why in certain models, for systems that are considered to be purely crustal, you also have some part that represent this reservoir that is deep. For example, here in origin gold deposits, you have the lampropheric melts here that could be a reservoir, but also, for example, for kaolin deposits, here you can see that this whole part represents the input of the lithospheric mantle. And so to look at this kind of input, we tried to make a connection between the two cratons in Canada, so the superior craton, of course, and the slave craton. So we're going to be looking at two different locations today. The Elliot Lake location, which is south of the superior craton here, and the Thor Lake location located south of the slave craton. So first I'll be talking about Elliot Lake. In Elliot Lake, we're looking at mantle xenolith, and specifically base and critical metal reservoirs that can be found there, because we know there are already resources there. It's known to be an uranium deposit, but also have a certain amount of rare earths and niobium. And we know that we can link this to the mid-continental rift events at 1.1 GA. So Elliot Lake, as I said, is located south of the superior craton. To give a zoom here, so Elliot Lake is specifically north of Lake Huron, close to the city of Sudbury. And in there, you have mostly granitoids, Proterozoic metasediments, and mafic dikes. Certain mafic dikes do bring xenoliths to the surface, and this is what we are looking at. So this is typically what you can see here. You have the xenolith, which is spinel lazulite in our case. This is what you see in the photo B with olivines, clinopyroxene, autopyroxene, and spinel. And the host is lamprophire. So on the suggestion of someone in the audience in the previous Metal Earth meeting, we dated the lamprophire, and it was a very good suggestion because now we know that it is younger than expected. It's at 1.1, which is perfect for us because it's coeval to the mid-continental rift event. So we're confident that these samples are reflecting what is happening at that time. We also dated the xenolith itself. So here you have in the x-axis the ages, All of these represent the ages of the Xenolith. So it's a wool rock. And we did Elliot Lake, Kirken Lake, and Wawa. These three locations are very close together in the south of the Superior Craton. We can see that Elliot Lake represents in green very well the Mid-Continental Rift event. So this is great for us. But this Mid-Continental Rift event is also seen in the other locations of Wawa and Kirken Lake. And this is very interesting to have finally a very nice snapshot of what would be the metal input during that event, and is also reflected in other locations at 1.1. So what is happening in these samples? We see that we have a lot of remobilization. We see it from mineral geochemistry, typically olivines. Here we have the Mg number on the x-axis, and you can see that the chemistry of the Elliot Lake sample is shifted compared to what would be expected in other cratons. So this is one indication. Also, if we look at the wool rock data with aluminum in the x-axis and calcium in the y-axis, we can see that we have this trend that shows very well the remobilization of our samples with a mix of melt depletion and also metasomatism that would enrich our sample. The amount of the two is very difficult to define because they're probably all a mix of the two processes. This is also what we see in the PGE patterns. So PGE stands for platinum group elements. This is all the elements that you can see here on the x-axis. I've put there two typical patterns so you can see what we're looking for. In red, this is a typical met depletion pattern. And the horizontal one here in orange is a typical metasomatic pattern. So you can see that our samples, which are in green and blue, are in between. So we have a certain amount of melt depletion, but also a very big input of metasomatism that is responsible for the enrichment in rhenium here. From mineral chemistry, we tried to understand what type of metasomatism is involved in our samples. And this is very well seen with the clinopyroxenes. Here in the x-axis, we have titanium, europium, and in the y-axis, lanthanum, ytterbium. And this nice diagram from the literature helps us define that there is an input here for the blue samples of a silicate metasomatism, a kimberlitic melt, and for the green one, something that would be a carbonatitic metasomatism. And we have seen from our samples that this carbonatitic metasomatism here is actually linked to the enrichment in rare earths, but also in niobium. We tried to see in our samples if there were any other metals that could be enriched compared to what would be expected for such samples. So we measured different metals in each mineral. So for example, olivine, orthopyroxene, and clinopyroxene, but also as wool rock, and compared this to the reference spinel peridotite value. So the gray boxes here represent the Xenolith value, and the shaded area would be what would be expected. So you can see that for the sum of rare earth elements, lead, niobium, and uranium were above what would be expected for this kind of samples. So we do have a reservoir that is created by this metasomatism that is induced by this event at 1.1, which would be the Mid-Continental Rift event. Now, considering what phase would be the carrier of such metals is difficult to say, because so we can see that, for example, if we look at the rare earths, each mineral has a different amount of rare earths, but what is the main control of this is actually the partition coefficient of rare earths in between each of these minerals. So that's why there is a difference, main carrier being clinopyroxene. But what is interesting is that for each of them, there is a large span of values, which means that all of them have been impacted by the metasomatism and had an enrichment. So in conclusion, we can see that there is some metasomatism defined as carbonatitic that is responsible for rare earths and niobium enrichment. Maybe uranium is not directly linked, but we know from the literature that in the Lake Superior here, in this area specifically, you can see the yellow dots, there are deposits that are known to have uranium, niobium, and rare earths elements. And what we think is that the thinning during the mid-continental rift events created remobilization and metasomatism that created a reservoir that we can see is defined in the Lake Superior, but actually extends to the area of Elliot Lake, which is east of there. Actually, here is the beginning of Lake Huron, so we're not that far from this zone. And that this reservoir should be around 100 kilometers depth. So this is really interesting. The second part of this talk is about the Salt Lake rare earth mineralization, and specifically bastnasite dating. So Salt Lake is one of the biggest rare earth deposits in North America. And so we thought it would be interesting to look at bastnasite dating and to try to apply it to other deposits in North America. So where is Salt Lake? Salt Lake is right here. It is associated with alkaline rocks, specifically cyanite. It has a very big resource. It's the third biggest in North America. The ore minerals include eudialyte, xenotime, gadolinite, monazite, and rare earth carbonates, and among them bastnasite, which is the mineral of interest today. So Salt Lake specifically is in a zone where we have alkaline rocks of age of 2.1, 2.2 million years, and specifically the Grace Lake cryolite, Salt Lake cyanite, and here you have the wall mineralized zone that is defined as being hydrothermal, so posterior to the magmatic input. This is how the sample looks like. So on the right, you have the hand sample, actually a big hand in that case. And you have mostly quartz, and all the red crystals here are rare earth minerals. So it's very, very rich. These red spots that you can see are actually former minerals that have been completely replaced by fluids to remobilize all the rare earth minerals. And so here, for example, on the thin section, you can see, so this is the former crystal. We can still see the shape. All of this has been completely altered, and all of that has become bastnasite and perisite, which are two rare earth carbonates. So this is the model at Salt Lake. You have several magmatic impulse that's in place, two different zones, one rich in zircon, one rich in eudialyte, and all of this has been remobilized by several metasomatic events that remobilize all the rare earths. So this is how it looks like. If you remember the edges of the crystals that we see on the thin sections, typically what we can see here, this is a map done with the microprobe. And so we can see that inside we have a lot of alteration. All the reds and pink is bastnasite. All of this is altered into this orange thing that is perisite. And after that, you have another input of bastnasite on the edge. So for this work, we decided to focus mainly on the bastnasite that is on the edge because these crystals are cleaner, and for a dating work, it's going to be easier for us to know what we ablate. So here I've put the composition of bastnasite and perisite. So bastnasite, the pink and red stuff, and perisite, the orange. You can see that this is minerals very rich in cerium and lanthanum. There is also a good amount of neodymium, which is very interesting for us because it means that we're going to be able to work on neodymium isotopes to try to trace the source. And the main difference between the two is actually the amount of calcium here. So this is going to be our tracer mainly to differentiate whether we are ablating bastnasite or perisite. So this is what you can see here with the rare earth pattern. It's very similar between the two. So we focus mainly on calcium to try to differentiate the two minerals. And we were thinking, well, since we want to date these minerals, is there a remobilization of uranium, lead, or thorium during these alteration? So this is why we made these diagrams. So you have calcium in the x-axis and uranium, lead, thorium in the y-axis. And we see that there is indeed a remobilization of these elements when you alter bastnasite into parasite. This is typically the dashed arrow that you can see here, but it's quite minimal. The other very interesting thing that we see is this vertical trend here for uranium, thorium, and lead. And this reflects the zoning of these elements in the bastnasite crystal itself. So you have a zoning during the crystallization. And this is very well known actually for carbonate samples. And it's been described in the literature and how to date this kind of minerals, considering that you have this zoning. So this has been described by Roberts and collaborators in 2020. Here you can see different pictures that they've shown in their paper. This is maps of uranium. And you can see that in different type of carbonates, you have a lot of variation from 1 to 3 orders of magnitude difference in a crystal. So that's very big. And so they defined a specific protocol to be able to date carbonates even if we have this variation. And the protocol is to look at a crystal like this one. You gotta make a transect from the core to the rim. So go through all the different amounts of uranium and the different amounts of radiogenic and common lead. And from that, you're gonna be able to trace this isochron here on the Terra-Wasserburg diagram, and the lower intercept is gonna be your age. So this is what we're trying to do here. But that we still need standards, of course. So we took 2 carbonate standards from the literature. The first one is WC1. It's a calcite defined by Roberts and collaborator in 2017. The age has been defined in literature at 254, both by LICMS and IRMS. Here, this is the data that we got for this sample. We're actually in good agreement with the literature, so we're happy about that. And the second standard is K9, which is specifically a bastnasite, so a rare earth carbonate. And it was described by Lee and collaborator in 2020 at 116 and 118. So with the 2 methods, they got a little bit of a different age, but this is very close. And for our study, we got an age of 118. So this is in very good agreement. Both of these have been dated using a NIST standard. So one thing that we can hint with this is that it doesn't seem to have a lot of matrix effects while dating carbonates with our setup. So this is quite a surprise and very interesting. So from that, we tried to date the bastnasite of Thor Lake. So at Thor Lake, the age of the mineralization is supposed to be 2.1 million years old. It's actually the age defined for the Thor Lake cyanide, which was dated by uranium lead on zircons, but it's said to be considered to represent the age also of the rare metal mineralization. But we know that the mineralization is actually autothermal and post-dating the cyanide. So the big question was, well, what is the age, and is it actually enriched a lot later or not? And so what we see here is that we took different grains, we did the transects, and we traced these diagrams, and we have an age of 1.9 million years old, billion years old. And this is consistent with the K9 standard and the NIST standard. We get more or less the same age. So indeed, there is no matrix effects, which is great. And we have an age that is a lot younger than what would be expected compared to what we see in the literature. And so it makes a lot of sense saying that you had first the magmatic input with the cyanide and then remobilization of rare earths with hydrothermal fluids. And this happens more than 100 million years later. Here we have an MSWD that is quite high because we still need to screen more our data. This is like brutal data that we extracted from all the dots that we did on our samples. But this is very promising and in good accordance with the literature. So here, the conclusion for this specific project is that we have the covenant dating setup operational, which is great. The Salt Lake bastnäsite might not be the best candidate for its standard, mostly because you have a lot of zones that are altered. But we're going to have the next try with another bastnäsite that we got from collaborators from Mountain Pass. The rare earth mineralization in Salt Lake is indeed a lot younger than the intrusive magmatic source, which is interesting, and more than 100 million years younger, actually. So that's a big gap. And the following for this project is going to be to do the neodymium isotope to try to trace the source. So overall, for this presentation today, what I want to say is that most of the rare earth deposits in Canada are actually located in the two cratons, so south of the Superior Craton and south of the Slave Craton. Today, we talked about Thor Lake, but actually there are a lot of other deposits that are not on this map that extend to the north of Alberta and north of Saskatchewan. So this is very interesting to try to compare the two zones and try to understand where are the reservoirs. In both Elliot Lake and Thor Lake, what we can say is that there is an impact of metasomatism and fluids either in the mantle or in the crust, and these can be assessed. And it is going to be the reason of enrichment in both cases. So that's why we try to put a focus on this one. Thank you.
Great, thanks very much, Helene. We have time for questions. Bruno, you have your hand up?
Yeah.
And I have my microphone off. So what triggers the carbonatic metasomatism? I know it's related to rifting, but are we looking at like CO2-rich fluids or gases from an underlying plume, or what exactly is this carbonatic metasomatism?
From the Xenolith itself, I don't think we have actually a proper insight into answering these questions. Maybe Graham has an idea of his own. Personally, I don't know.
Okay. The reason I'm asking is because it's related to a question from yesterday, is that at the steep rock sequence, which is early Neo-Archean, it's a good rift sequence, and then the ultramafic rock, which is a ferropicrite, is thought to be related from an enriched mantle source because of its enrichment in light rare earth element, and that looks so similar to what you're describing, but so much earlier. So I was interested, like, what could be causing this carbonatite metasomatism?
Well, I can chip in, Bruno, if I may.
Yeah.
Yeah, I think so. That I mean, that type of melt forms really specifically under very thick lithosphere from carbonate-rich mantle that's very close to its solidus. So you don't need much of a perturbation to trigger it. So it can be related to plumes where you might expect it to be some of the earliest manifestation of plume activity, just because that mantle is the closest to its solidus and will melt first. Those melts have a very low dihedral angle, so they migrate very effectively through the lithosphere. and have a great capacity for even though they're reactive. If they appear to migrate far into the lithosphere, carrying a lot of metal. So they could be related to plumes, but you don't need a plume at all to get that type of metasomatism, just minor thermal perturbations, or, for instance, some, say, edge-driven convection that might give you a slight amount of thinning at the edge of lithosphere. And note that all those rare earth element deposits are on the edge of the thick craton. So it goes back to this association between these types of mineral deposits and the edges of very thick parts of the craton. So the triggers can be varied, but it's related to melting of carbonate-rich mantle, ultimately close to the lithosphere-asthenosphere boundary.
Okay, is that published, Graham?
There are various reviews of that. I mean, I could send you some of that. Yeah.
Okay, that would be great. Thank you.
Yeah.
Can I ask a question? This is Dick.
Sure, Dick.
Yeah, I was looking at your geochronology and having done a lot of this stuff. You know, a lot of your points fall below the line. The line is constrained by the stuff down by the lower end of the Terrawasserberg Concordia, and the one point that's on the upper end. So have you tried to bin your data? Because the stuff closer to Concordia has a much better analytical uncertainty rather than some of the points off that are down. All the points down are really what's driving the regression line to younger ages. So have you tried to bin that? Just look at the stuff down at the lower part, because it looked like the analytical data is much tighter. And you might look at, say, looking at the size of the uncertainty versus the uranium content or whatever, or 6-4 ages or something, because there's the corrections may be getting, giving you all the scatter. So anyways, it's just a suggestion to look a little closer.
Can I take that, Helen, please?
Yeah, absolutely.
So I mean, in normal circumstances, yes, you would do that. Well, first of all, that was a really unfiltered pass at the data.
I appreciate that. That's what I'm asking. Yeah.
But with these carbonates really fall in the category of very high common lead minerals, yes. And so actually the best tactic is to use that to your advantage and use the leverage that the variable amount of common lead gives you to get a better regression on the Discordia line, because it's very rare that you will find with carbonates things that are very concordant. So you flip the situation and use that to your advantage, and that's why the laser. I mean, people have been trying to date carbonates by TIMS for years, and the problem has been that as you can see in the SEM image, there's so much disturbance and so much variation in common lead, it's very difficult. So the laser allows you to exploit that variation to your advantage, actually.
No, I appreciate all that. I was just looking at the data, and so many of your points, your ellipses, are down underneath that. And by including those in the regression, it actually is leveraging all the ages to a slightly younger intercept. That's all. Okay. Yeah, that's all. And so I was wondering if you tinkered with it a little bit, it might not be so much different.
We will for sure. So we'll come back to you next year on that.
No, fine. Yeah.
All right. Thanks very much. Thanks, Helen.